So welcome everyone to another LEAF seminar. So today we will have Hugo Messias talking about the ALMA observations with the Event Horizon Telescope. So Hugo obtained his PhD in 2011 at the University of Lisbon in Portugal. Afterwards, he went to Chile as an ALMA postdoc. In 2014, was awarded an EHT fellow at the Institute of Astrophysics and Space Science, where he was also a lead scientist of the Portuguese ALMA Center of Expertise. Hugo moved back to Chile in 2016 as an ALMA fellow with a short period at the end at 2019 at TA. But since January 2020, Hugo has become an astronomer at Alma's Department of Science Operations. So his scientific interests are most related to extragalactic astronomy, galaxy and supermassive black holes evolutions, gas content and dynamics, galaxy growth mechanisms, and so on. So today we will hear about the scientific and technical status of the ALMA observation. So please, Hugo.
So thank you, Liliana, and thank you for the invitation. Of course, it's nice to show back to Portuguese institutions what I've been able to get involved with all this time at ALMA. It's an exciting time to actually be here in witnessing these developments and be part of this group specifically at ALMA. So basically the team is mostly comprised with fellows. I mean, but also with staff now. That we've been having outside people like Lynn Matthews and Jeff Crew, which were basically the brains behind enabling ALMA to work as a single dish in the networks, both with EHT and then GMVA. We'll see what are those later on. But then we also had Chiraco Godi and even Marti Vidal, which helped a lot with ALMA data processing. And actually, some of these slides are from them. And then I mean, I started as a fellow in this, and now I'm a staff, and I'm leading this group from the ALMA side. But before it was Violette Impellicera, which I really appreciate all the teachings that she provided me with. And now I have my good friend David Robredo working with me, Ruben Herrero, who also was from the beginning here, also as a fellow. Now he moved out of astronomy, unfortunately. And then we have other fellows, Marilou, Belen, James, and Miguel. So it's a big team, but also very dynamic in and outs. So basically, I'll go through why do we need millimeter VLBI observations? What happens with the phased ALMA observations with EHT and GMVA, scientific results, M87, Sagittarius A, CenA, 3679. I actually added just briefly also another result on OJ287. And then future capabilities of millimeter VLBI, standalone phased ALMA observations. Basically, this is when ALMA is phased up, but only following its own schedule. And this is mostly targeting pulsar science, so timing science. And then if there are students in the audience, I'll go through some the opportunities to actually work with ESO and of course ALMA. So you've heard about GMVA, which stands for Global Millimeter VLBI Array, who operates at 3 millimeters, and the EHT, Event Horizon Telescope. You also hear about Event Horizon Telescope Consortium, and it operates at 1.3 millimeters. These are different stations. Sometimes there are stations that participate in both type of observations, but what I go through this is why we need this array and how do we go from this to that and why. Okay, so I'll go a bit back. I mean, hundreds of years before Tycho Brahe had that very famous mural quadrant, you had Abu Mahmoud Kojandi and Ulugh Beg with these 20-meter and 40-meter radius quadrants in Iran and Kazakhstan. I mean, I mean, this was back when amazing to have this, and as contrary to Tycho Brahe, I mean, the goal here was to actually observe the sun, but with that was basically to understand the magic of what we knew about the universe that back then. And it's amazing. You should read about this, what they've done, and another curiosity: why is it underground? And currently, what we know about it, this Ulugh Beg Observatory is actually underground. So it's amazing if you read about it. But then our knowledge continued, and then we reached the 20th century, and where you had the proposal of general relativity by Albert Einstein. Right from the start, actually, the first proof that it was applying well, this theory, was the precession of the Mercury's orbit. But then you had also the very famous solar eclipse, which allowed to see that the shift, apparent shift of the stars was greater than that predicted by the Newtonian, so you had to apply the general relativity. And then you had Karl Schwarzschild, which we will hear a lot in this talk, his name, which basically during World War I, while computing the trajectories or ballistic trajectories in the war, he was also getting Albert Einstein's equations and actually deriving and predicting that actually we should expect something that velocity escape is greater than the light, so it will be dark objects, which later on became what we call now black holes. But then also on that 20th century, starting realizing that, I mean, so many galaxies were out there, not just our own. And then we started organizing them in terms of luminosity, stellar masses, and we realized that the most massive ones actually were not as, in number-wise, were not present. I mean, galaxies were not increasing until infinity, basically. So there was a huge drop in terms of galaxies, which meant that we needed to have some sort of mechanism that will stop or slow or stop star formation in massive galaxies. Also in low massive galaxies, but that's another mechanism. But so I will focus on the one that actually then people came up with two sort of recipes, which was basically a radiative efficient thin disk around supermassive black holes. So black holes are accreting at close to Eddington and super Eddington accretion rates, and that radiation from the accretion disk induces some feedback, so it heats up the gas and does not allow the gas to form stars. On the other hand, you have these radiatively inefficient or advection dominated accretion flows, which is way less efficient. The disk is thicker, and it's associated with jets, like galaxy-size jets, going and piercing through the galaxy, and not only inducing too much turbulence, but also pushing the gas out of the galaxy, preventing star formation to happen. So the flavors that Riaf and Nadaf have been mostly proposed is magnetically arrested disks. So you have a strong organized magnetic field, and then you have the standard and normal evolution. So which you have turbulent magnetic fields where the radiation pressure from the disk dominates. So basically you had these mad, insane models or scenarios where people have been trying to understand which one is happening. And not only that, you want to know also how do jets form. So you have these two type of jet formation scenarios where you have the BP, so Blatford and Payne, and Blatford and Znajek models, which one is the jet comes from the disk itself, and then the other one is the jet originates from the poloidal region of the supermassive black hole. And you see those mostly everywhere in the sky. You see these very large megaparsec scale sometimes jets, which you could see sometimes from the X-ray, that you see that the induced cavity. So you can really see that mechanical pressure that we were talking about. So not only that, you also want to go even beyond the physics of the jets and whatnot, but in the supermassive black hole, but also test the Einstein theory of general relativity. And for that, you need to image the event horizon of those supermassive black holes. So how do you do it? And to what point can you actually do such a kind of study? So this is what we think that most AGN may resemble when you go down and resolve the system. Of course, cases have appeared that do not exactly hint for such a structure, but bear with me, I mean, this is a simplistic view of the universe that we are studying. So basically you have the accretion disk, you have the supermassive black hole, sometimes you have a jet, you have probably a clumpy gas and dust torus around at larger scales. But since it's dust and the accreting disk is actually emitting thermally at high energy, so you go through optical ultraviolet, and then this radiation goes a little bit outward and actually induces the X-ray corona. Okay, there's some boosting in the energy, and then you have this X-ray emission. But if you want to see those components, you have to pierce through all this dust around. It doesn't need to be a torus, but if it's cloudy and there is dust around, which is seen there's a lot of dust around black holes and everywhere in the sky or in the universe. So dust is present, so you need to pierce through. So if you actually want to, this section, if you want to get it, you need to go to the millimeter in the radio to actually pierce through and actually see the black hole inside. But not only that, I mean, the two cases that we believe that actually where we can see the shadow of their supermassive black holes, it's Sagittarius A star and M87 star. Those were from the start the two main targets, which were expecting a shadow size of 20 to 40 microarc seconds. So for that, to do that, in the millimeter and the radio, you had to have a Earth-sized telescope. I mean, of course, you cannot build such a disk, such a dish to do that. So you need an alternative. So basically, for you to have an idea what you need is actually, you probably heard this comparison is basically me being here in Santiago, trying to observe through the needle that you are holding there in Portugal, with the precision, with the precision of the size of the hole of the needle, but then the opening is the opening of these pans that we have. So the ring will be the size of that opening of the pan. So it's amazing what you can do. So no wonder that what the images that we got actually were so blurry, but it's the best that we can do so far. So you have these two networks that we talked about, 1 millimeter and 3 millimeters. And basically, how does that work? I mean, this is an image that I took from a room through a curtain, very thin thread curtain to the street. So you can see that the lights passing through that network actually induces this pattern, this interference pattern. So what I mentally can deconstruct this and see what's behind. You can see houses here. You can see the lights from the stars. Lights from the street lightning. So you can do it mentally. So basically, that's what we are doing. We, instead of a thin thread curtain with holes everywhere, what we have is actually just these holes that we have observation in the on Earth, and then we let the Earth rotate, and you start having more holes in this curtain. So basically, what you'll have is then the interference pattern, and then you need what we are doing just now. You need to reverse the whole thing, and you obtain the image. But for you to do that, you need to have a really good clock everywhere in these stations. So the tropospheric turbulence limits you to coherent timescales of below the 10-second scale. So, but then you have the rubidium clocks, you have the hydrogen clocks that actually provide you good time stamping in those hours. So there is no problem with the timestamp issue. The main issue is actually the frequency reference. So we are doing observations at around 90 gigahertz, 230 gigahertz. In the future, you will hear that we'll be observing 350 gigahertz. So that's really high frequency that you need to provide to each of these stations. So when you correlate, you know that you're phasing up precisely the signals, okay? So basically, the rubidium clock limits you to observations up to 16 gigahertz. So VLBIs, VLBI size baselines, you can do with rubidium clocks up to 16 gigahertz and up to terahertz observations with the hydrogen clock. So basically, all these stations, if they want to do these VLBI observations, they need the hydrogen clock or something with the same precision. The other thing that, especially for EHT, which is the higher frequency one, is very limited to weather conditions. And you have stations in the north, stations in the south. So what we do is this go-no-go approach where we have a 12-night window, and we trigger about normally 7 nights. So basically each night we go, okay, we have good weather in most of the key stations, we are a go. If not, we have a no-go and we don't observe. And it doesn't need to that ALMA is always present, like, because if ALMA is affected by bad weather, and if other key stations are okay, then it happened in the past that the network continued to observe and ALMA unfortunately did not join. That happened in the past, even this year. But that's because, I mean, you cannot have on Earth, you cannot have good weather everywhere at the same time. And that's why the observations are limited to April or October, but in this case, mostly to April for other reasons, April, March, actually. So, but ALMA is really the revolutionizing key in this network. Basically, what you have here is basically the correlated signal between each of these stations. So we have Pico Violetas, which is basically 30 meters in Spain. You have Apex, which is the 12-meter antenna in Chajnator right next to ALMA. You have SMA in Hawaii, LMT in Mexico, and SMT in the US, but I can't remember if it's Arizona or not, but okay. So it's this is basically the best that you can do in saying, okay, I'm finding signal between these two stations, and the signal is this one. So it is when you correlate, when you phase up the signals, you have this correlated signal, okay? And you have this one, and sometimes you have this noise. So it's not as clear. But the thing is, as soon as you add ALMA, which is this really big collecting area, so it's equivalent to having a 70-meter dish. When you put that bucket in the array, you can have really high signal to noise correlations with each of these stations. And as soon as you do that, as soon as you do with two, then those two will have a really nice correlation between themselves. And this is what happens, okay? As soon as you put ALMA, everything changes, okay? And it's just, you later see that it's not just the location to get proper imaging quality. That if it was that, you just need Apex. But ALMA is a huge, big collecting light collecting telescope, which allows to do this kind of referencing and improve much better the image quality behind that. And then there's another how do you say bottleneck, which is actually these things are recorded. So all the signal that comes goes through ALMA and goes through other stations is recorded and then shipped to Germany and US for correlation. But if you're relying on South Pole Telescope, for instance, you can only get these recordings during the summertime, and that basically delays the whole thing to December. I mean, you can start correlation in other stations, but the full thing is only until SPT has arrived to the correlators, and that happens only later in the year. So you're observing March, April, and you need to wait until the end of the year to actually have proper calibration. So first, let's go through the science. I mean, you know Messias 87, sorry, which basically is very famous because it has this huge, beautiful jet getting out of the galaxy. It has been studied through many scales and frequencies. Each of them is telling us different parts of the story. And I think, if I'm not wrong, Messias 87 was the first radio jet identified in the sky. And what is cool about it is that you can see it move. And this is just a span of about 6-7 months, and you actually see it moving with VLBI observations. So it's very active jet, almost at the line of sight, towards the line of sight, and basically when you pierce through the millimeter, you actually see the shadow. And that was what was presented in 2019 with observations from 2017. These are, for me and for many, are probably one of the, if not the observations that were more inspected ever. I mean, just from this data, 6 publications, actually later on in 2021, there were more, and the care that had to be taken in terms of calibration was huge. But then it's impressive what we get. I mean, this is a zoom in, so this is just the ALMA scale resolution or map that we see with the same data that we're observing in 2017. You have this image from ALMA alone, but then ALMA also works as a single station. It also sends the signal to the correlators and helps to create this beautiful ring, which has 42 microarc seconds with a width which is less than 20 microarc seconds, with more than 10:1 brightness ratio between the shadow and the ring. And basically, if you recall before, we were talking about, with M87, we were talking about an uncertainty whether it was 20 or 40 microarc seconds. So at first, people were not, were actually afraid that actually you will be observing M87, but the ring would not be observed, the shadow was not going to be observed because it could be 20 microarc seconds, which was basically the resolution of the array at the time. But luckily it's 40 microarc seconds at a distance of about 17 megaparsecs. It means that the black hole it's about 6.5 billion solar masses, which agrees with the stellar dynamics and not so much, and disagrees by almost a factor of 2, about a factor of 2 with the gas dynamics estimate. But as it's all, and many people say it's a blurred image, but it's the best that you can do. But what happens is that then, because of that, you have a lot of degeneracy. When you start describing physically this shape, you have many situations, I mean, many scenarios which could explain this ring. Not only the sane, but also the med. Then whether it's non-spinning or a spinning black hole. In these cases, you have a retrograde rotation, so the black hole is rotating one way, and the material around is rotating the other way. Then you have this Schwarzschild no spin black hole. And then you have the prograde. So both material and the black hole are rotating the same way, the same direction. So how do you break the degeneracy here? So actually, this first is the retrograde scenario is two variable. And actually, during these days from April 6th to April 11th, if I'm not wrong, you don't see a clear variability in the morphology of the disk in total intensity. On the other hand, the no spin scenario means you will not have a jet, and actually you see a huge jet. So you're left with a prograde scenario. But then there's a lot of things still to be told. One of the things was, what can we get more from the polarimetry of the ring? And actually, it tells a lot. So the polarized non-thermal emission dominates the southern region. So you have a very highly polarized part here, and it can be a contamination also due to the Doppler effect, because the material is rotating this way, and the southern part, and because it's inclined this way, basically, the southern part, it's coming towards us, and there's this Doppler boosting that then can induce this part, this contaminate, and induce this higher polarization, but then which you don't see in the southern part because it's not as brightened, so you don't have information there. But then the cool thing is that with this sort of shape of the EVPAs, actually it's telling us that it's a poloidal magnetic field, which is evidence for the BZ mode, where the jet has origin in the poloidal region of the supermassive black hole. Not only that, the same models were rejected. The accretion is from a magnetic arrested disk, which basically means, and the values is 1 to 30 Gauss, which basically, if you see, it's a fringe magnet, but it's not just a fringe magnet, it's this strong of a magnetic field at scales which are larger than the solar system. So yes, it's pretty strong, this magnetic field. And then you have a plasma density to 10 to the 4th or 5 per centimeters cubic centimeters, sorry. And electron temperature that goes beyond the billion Kelvin. But then one thing that the total intensity was not telling us too much was the amount of the accretion rate. And as soon as you actually input the information from the polarimetry information, then you narrow down the range of the accretion rate that we're talking about. And the estimate is about 3 to 20 times 10 to the minus 4 solar masses per year. That's about 100 to 700 Earth masses per year. But beware, just as a reference, the Eddington accretion rate is 140 solar masses per year. So as you can see, it's very inefficient accretion rate here, which is basically the ADAF scenario that we're talking about here. So I've mentioned this before, but I'll just reiterate the role of ALMA as a VLBI station. This is just based on location. If Chile, which means apex or Chile, or ALMA was not present, you won't see a perfect ring. You see just two elongated blobs. But then you have this phase steering that I was talking about. Here is a bit more clear as well. you go from something that has no phase steering with the help of ALMA to something that is phase steered with ALMA. And it's the difference is striking. So not only this allow the quality of the image that you have here. If not, you'll have all these phase errors and decorrelation that will not allow you to do this sort of science. So then what about Sagittarius A? That was the second, the other, actually people were drooling about Sagittarius A at first, but it's the hardest one to actually do this sort of imaging. So, but before, even in 2019, there was already a GMVA 3 millimeters of observations telling us that indeed, as expected, there is the scattering screen does not allow you to see the source, the intrinsic source behind it, but you can infer, and actually is resolved. So at the time we could already get some constraints on the nature and size of the source. So models including JET were only acceptable at low inclinations, so close to the Lano side. Thermal disk models were preferred, but wavelength and angle dependent as well. The models that GMRD models that were used actually needed improvement and still need. I mean, no, don't take me wrong, because they need to. I mean, in this case, specifically the 7 millimeter emission was not properly fitting the model, or the models were not properly fitting the size of the 7 millimeter, and it was just because the models were not left running for enough time for to have the proper disk properties, and it had to be wider, in the sense it had to be longer, because the emission at 7 millimeter, the resolution is bigger, so you're not resolving as much as the 1 millimeter and 3 millimeters. So you need 1 millimeter observations to actually do this kind of job. And we got this also from 2017 observations, but published in 2022 this year. And I think I think we are part of the generation that should feel lucky to see all this happening. Not only the gravitational waves, these two shadow of black holes. I mean, recently we had the JWST imaging. I mean, it's amazing the science that has been appearing recently. So what I will say about this image is that the bars here are not probability distributions, and this is not the time sequence. Okay, so you had this a similar image back in M87, where each of these four things were a day, and this is not the case. And the reason is this is just an example of the imaging approach. So you have the Dolomites here, and you see a cloudy day going through a clear sky, and you see all these evolutions during one day. And so depending on when you are observing at each time of the day, you'll see different morphologies, different obscurations, whatever. So what has been done was the team image each of these chunks, and then image and got all the library of images, and then it clustered in types of images. Okay, so. And then each of these clusters were averaged into 4 groups. So it didn't mean, I mean, it just the clustering, it didn't mean that it was a time sequence. And then you have all these averaging over these 4 clusters. So it's the same happened with Sagittarius A. You have all these time chunks that the team managed to create an image for. And then you have this algorithm that does the clustering, and so the groups are depending on where do you see the bright spots. So there are 4 groups. So you average out, but then you have the clustering, and there are 4 groups. Let me see, and there you go. One which is which has, I think I need to wait because, yes, one has three blobs, two bright on the west, one bright on the northwest, and then one bright on the east, and no clear ring morphology. Okay, this is the group with no clear morphology. It's not as frequent, but we do see chunks of time that it's not as clear. But don't feel disappointed, because what happens is that these are 2 days of observation, and the data most that have been presented are from one of these days. So you'll see that one of these days actually has a poorer image quality. And that's just the effect of one missing station, which was Pico Voleta. And just because of that missing station, the quality of the image was not as ideal. So that's why most of the results presented in this batch of other 6 or more than 6 papers actually based on April 7th. But the cool thing is that it's Sagittarius A, you have a lot of observations, a lot of constraints, and then you can, with that, you can break all the degeneracies, not all of them, but many degeneracies between all the models, between whether it's sane, whether it's math, whether it's spinning counter, so it's prograde or retrograde, the inclination of the system, and whether you have an emission that is dominated from the disk or from something that it's outflowing. Okay, so you have the EHT constraints are the source size, visibility, amplitude, morphology, which basically is telling us in the visibility plane where is the null, for instance. And then you have the ring width, diameter, and asymmetry. And then you have non-EHT constraints. We talked about the 86 gigahertz flux and size. You also have the 2.2 micron flux, which basically comes from VLTI. Then you have the extra luminosity. And then you also have variability constraints, which is the light curve that you saw in 230 gigahertz from ALMA and SMA, and also the visibility amplitude variability at at VLBI baseline scales. So at the end, actually, if you consider all these constraints except the integrated light curve from ALMA and SMA, the only models, the only combination, the scenario combination that you actually have is something that it's practically almost in the line of sight. So it's an outflowing, it's a system that it's pointing almost towards us. So it's with a 10 to 30 degrees of inclination. It is matte, so again, it's a magnetic rested disk, and the other thing is it has to be prograde. Now, these values that you see are specific values of the spin, so there was no like more finer details on the spin. So, but basically, it's a non-spinning prograde system, and this R high is telling us that there is the possibility that there is an outflowing jet as well. So yes, and then later on we also can infer the accretion rate, which in this case is less than a moon mass per year. And while for reference, the accretion, the editing accretion is almost 30,000 Earth masses per year. So again, we are talking about the ADAF scenario. So very inefficient, but this was known, of course. So what about the outflow, predicted outflow? I mean, if you see the amplitude, visibility amplitude, there is no excess from the emission to tell us, yes, there is a jet, an outflow contributing to the emission, to the ring emission. So whether it's, I mean, there is no clear evidence. It doesn't mean that it's not there. And how is it emitting? Is it emitting thermally, or is it non-thermally via cyclotron emission? So it's still unknown. So what are the evidences for such activity? So you have the famous Fermi bubbles, which extend up and down about 40,000 light years. Up and down, basically, and that's more than the distance that we are from the galactic center, for instance. So, and then there is also the evidence, possible evidence for these shock fronts being induced by this possible jet-shaped morphology feature, and then you have also the light echoes, telling us that 100 years ago, Sagittarius A was way more active than it is now. So it's not something that strikes us as completely revolutionizing, but it's nice to see that you have this independent evidence that indeed there is something happening there, and it's just not just an accretion disk around Sagittarius A. And it's and the cool thing is that again is rotating this way, and it agrees with the mini spiral arms rotation, so this way as well. So I mentioned you that those constraints were avoiding the light curve seen by ALMA and SMA. And actually, it's very cool. This is an amazing video done by Ivan Martí Vidal, which you show that basically the flux. I mean the how do you say? The flux reference was set to the mini spirals, and then you see the core oscillating in variability. And this size is different from what we see here are at sizes that are larger than what you see in the ring. So the variability from the ring, it's explainable by the models. They avoided going through the morphology variability because, as you saw, it was very complex to do this imaging, this adaptive imaging. But then you have these larger scales, and this kind of reminds me what you were seeing also in the 86 gigahertz. So it may be in this case that the models are too simplistic. The models are not large enough, for instance, or to consider all these kind of effects at larger scale. So this is something that still needs to be explained, this light curve from Sagittarius A. What happens is that the models at these scales predict more variability. And although we see it varying this much, I mean, imagine varying even more. So what about sizes and metrics? This is basically the comparison, the perfect comparison between the two in terms of apparent size. But then, of course, you know that M87 it's that size because it's farther, but it's bigger. The whole solar system until until Pluto's orbit and Voyager fits within the shadow size. And then you have the ring of Sagittarius A, which actually fits inside the Mercury's orbit. So two different scales, two different masses separated by 3 orders of magnitude. But the point here is that if you want to actually test the black hole metric, you better, it's actually Sagittarius A, it's on one side is better to study in that regard because the VLTI and KEGG stellar orbits provide a very nice estimate of the mass distance ratio. And if you recall in M87, you had that uncertainty of a factor of 2 between the stellar orbits and the gas dynamics. But since you have the ring size, you have the shadow size, then if the gravitational radius is depending on mass and distance. If you have these two, then by studying the gravitational radius, which basically you can infer from the shadows, from the ring size, then you can test the metrics, the black hole metrics. And it's not just the masses, that the different masses that Sagittarius A and M87 probe, is also the curvature versus gravitational potential parameter space. It's a whole new parameter space that it's being traced with these observations. And what you see here in this right-hand side plot is actually the probability distributions of different imaging and scenarios from the EHT characterizing the ring, compared to what is expected from the care metric. And this is about the 8% range inferred by the care metric. This is deviation from the Schwarzschild, so no spin scenario, to something that it's rotating, maximally rotating. And you see that the predictions are basically well in concordance with the care metric. Not only that, if you compare them with the gravitational waves, which have this non-stationary scenario versus the stationary scenarios in Sagittarius M87, you also see that regardless of the mass, black holes should have the same metric. So this is one of the biggest results also here, is that, I mean, you go from 8 orders of scale and you see no real difference between these two scenarios. So other EHT results, I'm almost finishing up, if I may continue. Other EHT results comprise, like, for instance, Centaurus A. This was totally revolutionized because Centaurus A is a southern source, and having ALMA improved dramatically the resolution that we have before. And this allowed to actually see very similar morphology with M87. So you have these edge brightened walls of the jet. You have the counter jet also from Centaurus A, and the event horizon shadow should be visible at terahertz frequency. So you remember that, for instance, the hydrogen measure would allow such sort of observations, but but you need the weather. The other thing was 3679. It's usually observed as a calibrator, but of course, then at this case you start seeing all these new things. So, and you can see that each of these boxes in the left is zoomed in on the right. And you can see that down, you'll see this morphology where you have some sort of a bright knot here, more extended emission, and then practically perpendicular to it, you have an extended emission practically 2 blobs away. What they've seen is actually they seem to be moving during the observations. And one would expect that this is where the supermassive black hole is present, but actually, if you actually see these movements of the centroid of the emissions, it doesn't add up. So actually, in the end, what might be happening is that the black hole is here, and you have a hugely twisted jet taking shape. Is it new? No, it's actually something that it has been, it's expected. And possibly it has been observed in OJ287. These are GMVA results. Depending on the imaging that you have, you'll see it or you won't. But the super resolution algorithm, which is allowed from EHT imaging and Smiley, you actually see a bit of a twist there. And possibly some emission on to the west too of where the supermassive black hole is here. So the twist here can be from a precessing black hole, either because this is an expected binary black hole, and it's one of the candidates to be emitting nanohertz gravitational waves. But it can also be just the jet interacting with the nearby interstellar medium. So More to come in future observations. So what's up with the future? We already have both active and passive phasing. So passive phasing means that we can actually observe with ALMA fainter sources. So already this year we opened that window. You have this fast mode, which basically allows us to phase up more efficiently with information from the water vapor radiometers. The GMVA, we are now being able to do spectral line VLBI, basically the SIO maser in band 3. That means that we will be observing the GMVA, and EHT this year next year we'll already be observing in band 7, which will provide us better detail on the imaging, because it's almost 1.5 improve resolution because of the frequency and more stations. And what do I mean by more stations? In 2017, observations were just the dark blue stations, specifically for the EHT. And then you starting adding up new stations. 2018, you already had GLT, Kid Peak, and from 2020, actually not 2020, 2021, you already had NOEMA, and this year as well. And in the future, we have this YAMA single dish in the north of Argentina, which is an Argentinian Brazilian project, and also the African Millimeter Telescope in Namibia, which is basically assessed that it's in La Silla in Chile, that will be transferred to Namibia. And that will provide north-south good resolution at the same time zone as the European station, which is definitely a major plus on that. As for the, if I may, Liliana, may I complete this, or is already too extending too long?
Yes, go ahead.
Okay, so the standalone phased ALMA, again, it's ALMA phasing up and observing by itself. We can be doing all these observations also in VLBI. We can phase up to, say, normally 40 antennas, which basically means what I was telling you, 70 to 80 parabolic dish, which is amazing collecting area. And then how do you do this? It's basically you have a system which allows you to do online self-calibration. So based on these bright sources, you are pointing to the source, and since they are point like at these scales, you just assume that the source needs to be continue to be point like, because you know, and then you correct, and all the effects that are deviating from that, it's just because of the atmosphere, and you correct for that, so you get this phased up signal. But the one of the major applications is the time domain studies, and basically pulsar, and you try to infer the emission mechanism. So does ALMA still see coherent emission that you see from the radio regime, that but you don't see it at high frequencies, so shorter wavelength? So actually you still see, so ALMA, depending on the frequency, you still see that it continues this coherent spectral, so the spectral index of the coherent emission, although sometimes you see this is a binary case where actually band 3 sees the coherent emission, but then ALMA band 7 sees the disk of a neighbor star. So, but we already have this example of VELA pulsar where the ALMA managed to have the precision, the timing precision of 100 microseconds, and allowed to see this delay, 1.8 millisecond delay on the pulse that you see in multiple frequencies. So the main pulse is seen at about 1.4 gigahertz. And then you see the second component, which is from the conical shape. It's induced by the conical shape of the pulse of the pulsar. And this has, I would say, that has definitely other applications. So complementarity with SKA when it comes online. SKA can search for millisecond pulsars, or ALMA does it, and ALMA follows up to see this delay, for instance. So many applications, and it's also using pulsars as detectors for gravitational waves. So exciting science ahead. And I'll just finishing up with the easy opportunities for early career scientists. You have the fellowships, you have the studentships, and you have the internships. These are different levels. So for fellowships, you have to have a PhD. Studentships is basically you do part of your PhD at ESO, either in Germany or Chile. And then you have the internships, which are basically 2 to 4 months projects with staff like I am. And I'll finish there. Thank you. And sorry for the delay.